All right, hello, welcome to today's seminar talk. Our speaker today is Cranston, and he will be speaking about most six regular toroidal graphs, and all colorings are Kempe equivalent for them, I guess.
Cool. Well, thanks for having me. I wish I could actually be there with you guys in Ames, but this will work for now. Okay, so I'll tell you what all these words mean in a minute, but we'll kind of build up to it. I should mention all of the stuff that I'll talk about today is joint work with my PhD student, Reem Mahmood. So let's start with Kemp swaps, and this is a definition, but it's maybe easier if I just show you a picture. So in the discrete math seminar at VCU for a long time, we used to say, whenever you give a talk on graphs, you have to have the Peterson graph somewhere. So this is my Peterson graph. So the Peterson graph is 3 chromatic. There's a 3 coloring. So here's one example of what you can do with a Kemp swap. You take some component of this graph induced by orange and blue. So in this case, it goes down to there, and then you sort of swap the colors on it. So everything that was blue becomes orange and vice versa. Another thing you could do is this. So this is another one. This is just the green-blue component right here. It's just size 2. So you just swap it. And another thing you could do is you could just simply, if you have a vertex where orange in this case, or green in this case is missing from the closed neighborhood, and you can just recolor it with green. So any color that's missing from the closed neighborhood, you can just recolor the vertex with that, and that's fine. So these are sort of 3 examples of what you can do with Kemp swaps, and this is the formal definition up here. All right, so let's just start with some examples of how Kemp swaps have been useful historically. So the 5-color theorem is really quite easy to prove, and you've maybe seen this before, but let me just give you a refresher that fits easily onto one slide. So we're going to go by induction, and we've got a vertex of degree at most 5 by Euler's formula. And if it's degree, so you're going to color, you delete V and you color the rest by the induction hypothesis. And now you want to extend the coloring to V. So if V is only degree at most 4, then there's some color that's missing from its neighborhood, and so you can just color it. So you assume that it's degree 5, and also you assume that the colors on all of its neighbors are distinct. Otherwise, you can just give it a new color. So this is sort of the hard case, this is the interesting case, and we want to modify this coloring a little bit before we have a coloring for V. So the thing that you want to try to do is you want to try to do a Kemp swap here at vertex 1. So what does that mean? So the 1, 3 component, so this vertex 1, so in this case 1 is green, vertex, you look at the component induced by colors 1 and 3 that contains vertex 1, and you'd like to swap the colors on it so that now this is colored with color 3, like that. And then if that works, then now this is color 3, and so color 1 can go on V and you're done. But the place where this is a problem is maybe this component also contains W3. So when you swap and W1 gets colored purple, now W3 gets colored green. And so you didn't really actually make any progress. But this is actually not as unhelpful as you might think, because now what you can do is you switch and you recolor this vertex 2 with color 4. And the point is that this 2 and 4 can't be in the same Kemp component, the 2, 4 Kemp component, because they're cut off by this 1, 3 path. And so by planarity, you can't cut through here because you would run into this path and you'd have to have a vertex that's colored both green or purple and orange or blue. And so if 1 and 3 are connected, then 2 and 4 can't be. And so then you can do the Kemp swap and you can color V with orange. And that really is kind of the whole proof. I'm not really sweeping much under the rug there. So that's one place that Kemp swaps are useful, and that's sort of where they first arose historically. technically they arose first when Kemp tried to prove the four-color theorem and failed. And nobody realized that he had failed for like 11 years. And then someone came along and said, actually, that doesn't work, but you can salvage it and do the five-color theorem and this proof that we just saw. You can also use Kemp swaps to give a short proof of Brooks' theorem. And Kemp swaps are actually really useful in edge coloring. And one thing that's nice about edge coloring is all of the Kemp components in edge coloring are either paths or even cycles. And so you have a lot of control. Like if you change the color at one place, it's only going to mess things up at most one other place. And so that gives you a lot of power. If you haven't thought about it before, edge coloring, you can think of it as coloring the line graph of the original graph. And so the fact that line graphs don't have induced claws, that's what gives you so much control in edge coloring. So anyway, okay, so let's talk about Kemp equivalence. So Kemp equivalence is actually one of the terms in the title, so this is a good thing to define. So basically what Kemp equivalence means is if you have two colorings, phi1 and phi2, then you can sort of get from one to the other by a series of Kemp swaps, never using more than the K colors. So a simple example is the Peterson. I showed you a few of the three colorings of Peterson, and it turns out that all of the three colorings of Peterson are three equivalent.
Dan, if you can hear us, you froze.
Independent sets of size 4. What would you say?
You froze there for a bit. Could you go back 30 seconds or so?
Sorry, you're cutting out. I think that's Ryan, but you keep cutting out.
You froze briefly.
Oh, I'm sorry. I froze.
I agree with
am
Ryan.
I good? Am I good now?
I think so.
All right, we'll keep going, and if I freeze again, then we can try something else. So what I was saying was just that this is a simple example of a graph where all the three colorings are Kemp 3 equivalent, and it just boils down to the fact that the three colorings are in a sense defined by this color class of size 4. And there's not very many of those in the Peterson graph. And so you can get a quick understanding of what things can look like. But let me give you another example. So this is maybe even a simpler graph. K3 box K2 is this prism. And here are two three colorings that are not Kemp equivalent. So if you look, let's look at the one on the left for starters. Say that you do a blue-green swap. Now you'll get a different coloring, but it's sort of not really different in the sense that the color classes are the same, right? So you've changed the names, you've changed which vertices are green and which vertices are blue, but they're just sort of interchanged, right? And so the point is, any Kemp swaps that you do on this graph, this coloring in the left, they're going to preserve the color classes. Which vertices get which color are going to swap, but the color classes themselves, that set of three independent sets of size 2, that's going to stay the same. And so you can never move from these over here to these over here. So why would we want to be interested in studying K equivalence of colorings? Well, there's a couple reasons. One, I'll give you sort of a in practice answer, and that is for sampling. So a lot of times we're going to be interested in saying, what does a typical K coloring look like? And it's usually the case that there are lots of these K colorings, and so we don't want to enumerate them all. And so we'd like to just be able to sort of pick one uniformly at random. And so the first step in doing that would be to say, is there a way to sort of generate all of them, even if it's not necessarily uniformly at random? And the answer is yes, if all of these colorings are Kemp equivalent. So what you do is you sort of build a Markov chain where each of the states in the Markov chain is one of these K colorings. And then the transitions in the Markov chain are moving from one K coloring to another that differs by a single Kemp swap. And so what you do is you start with one Kemp swap, you start with one K coloring, and then you pick uniformly at random some component, and then you swap that component. And you want to know, can I get to all of the other K colorings starting from here? And then if the answer is yes, then you get into questions of, does this chain mix rapidly, and is the stable distribution, is it uniform? But so that's sort of a slightly more practical one. From a sort of more theory side, when you're trying to K color a graph, if you're trying to do it by induction, so we sort of saw this in the instance of when we were proving the 5-color theorem. If you're trying to do it by induction, you have some K coloring of the smaller graph G minus V, and it's not something that allows you immediately to extend to V. Now, if you believe that the whole graph G has in that case, a 5 coloring, then when you delete V, you certainly have a 5 coloring of G minus V that will extend. And so the question is, can you sort of get to that one, that 5 coloring that will extend? And if you know that all the 5 colorings of the smaller graph are equivalent, then the answer is yes. You'll always be able to get there by a sequence of Kemp swaps. If the answer is no, then that might give you pause when you think about trying to do your proof that way. All right. So what is known so far about Kemp equivalence? Well, the first lemma, so this was proved by Las Viernes and Meyniel in 1981 is when it was published. And it's a very simple statement, but it turns out to be really useful. So what it says is, if you're interested in K colorings and you have a vertex of degree less than K, and you want to know if all the K colorings of your graph G are equivalent, then what you can do is you can simply delete that vertex. And if all of the K colorings of the smaller graph are equivalent, then all of the K colorings of the larger graph are equivalent. And the idea there, it's a very simple idea. Suppose that you can show that all of the K colorings in the smaller graph are equivalent. Then when you take any two of them, there's some sequence of Kemp swaps that will walk from one K coloring to another in the smaller graph G minus V. And the idea is just that we want to extend these colorings of the smaller graph up to include this vertex V that you deleted. And the intuition is that because the degree is less than the number of colors, you're always going to be able to do that. And there's sort of two cases to think about. One is if all the neighbors of that vertex that you deleted have different colors, well, then you have some color to put on, and that's fine. And it's sort of the end of some Kemp component. The other one is, well, what if there's some repeated color in the neighborhood? You could be worried about possibly merging two Kemp components. But the idea there is, if you have sort of accidentally merged two components because you have two neighbors that are the same color and you're the other color that are both involved in the Kemp swap, then you can just recolor that vertex with something else that's not involved in the Kemp swap, because again, its degree is less than K. So that's a simple lemma, and I've basically given you the whole proof, but it turns out that it's actually really useful. So one immediate consequence is that if G is D-degenerate, then G is, and I'm calling it K ergodic, but what K ergodic means is just what I've said here. All K colorings of G are K equivalent. And this is just, the proof is just by induction using this lemma repeatedly. And so in particular, it tells you that if G is planar and you're interested in colorings with more than 5 colors, then they're all going to be K ergodic because planar graphs are 5 degenerate. So this, I think, a really nice result, and this was proved by Meyniel in the late 70s, and I think it's maybe not as well known as it could be, partly because the proof was in French. I think this was one of the last papers that was published in JCTB in French, but it's a pretty proof, and again, it's like a lot of these proofs, it goes by induction, and you can assume the min degree is 5 because if it's less than 5, then you can just win by this lemma up here if you have a vertex of degree 4 or less. And so the idea is sort of, let's see if I can draw a picture real quick. Let's say you've got a vertex here of degree 5. So if you've got, so the idea is you've got some color that's going to show up twice in the neighborhood just by pigeonhole. And so now if you're trying to get to some other coloring over here, and you've got a different neighbor that shows up on those same two neighbors have a repeated color, then it's actually fairly easy. What you can do is you can essentially just contract these. You can contract those vertices, those blue vertices, here and here onto this vertex, and these guys here and here onto that vertex, and then you just proceed by induction. And so sort of the more challenging case is if you've got something like, let's see. Oops. If, say, instead your repeated color green was maybe here and here. So this is more challenging, and what you end up doing is you kind of have to find some intermediate coloring where you have a couple pairs of colors that are repeated, and you sort of use this idea of going from here to here, and then you swap and you go to sort of a different pair that's like this. So there's some really nice ideas. I'm not going to belabor it too much, but I definitely recommend that if you're interested in this stuff at all, you go back and try and read that proof. If you're curious, I have an English translation if French is not your métier. So the next thing I wanted to mention was, so Meyniel proved that planar graphs are 5 ergodic. And so the natural question is, are they 4 ergodic? Or is it true that for every planar graph, all of the 4 colorings of that graph are Kemp 4 equivalent? And the answer that Mohar proved is in fact no. And we'll talk about that in just a little bit. But he did show that all planar graphs are chi of G plus 1 ergodic. So when the planar graph is 4-chromatic, then that's just a consequence of Meyniel's theorem. If the planar graph is bipartite, it turns out that that's actually really pretty easy. That's like an easy homework exercise. So the interesting thing that he had to work out was showing that if you're 3-chromatic and planar, then all your 4 colorings are Kemp 4 equivalent. So I guess as I'm going along, I should maybe just pause and see, does anybody have questions? Is this stuff kind of making sense, or no questions in the chat? All right. Okay, cool. So I mentioned that planar graphs are not 4-ergodic. They're not all 4-ergodic. And so
Well, actually, Dan, can I interrupt a second?
Yeah, sure.
Mohar's proof for the last part. So all planar G are chi of G plus 1 ergodic. It occurs to me that that theorem probably does not require knowing the 4-color theorem.
No, it does not.
That's interesting.
So let's see. So the point is, no, it definitely doesn't, because if you're, let's see, what do I want to say? If there was a planar graph with chromatic number more than 4, then it would immediately follow from this statement up here.
Okay.
Right? This is sort of a trivial one that you get just from the degeneracy.
I see.
And so then for the graphs that are 4-chromatic, you have Meyniel. And so what he proved, basically the whole point of this is just that if you're 3-chromatic and planar, then you are 4-ergodic.
Okay, thank you.
Yeah. Okay, so planar graphs that are not 4-ergodic. So we saw these, and these are planar graphs that are not 3-ergodic, right? So you have 2 3-colorings, and they're not Kemp 3 equivalent. And so now to build planar graphs that are not 4-ergodic, what are we going to do? And we'll do this. We'll just put a new vertex that's sort of inside of each 4-face that dominates all the vertices on the boundary of that 4-face. Now, when we were trying to show that this graph was not 3-ergodic, the argument was simple. It was, no matter what Kemp swap you do, you're going to be stuck with all the same color classes. Like which color is actually used on that class will change, but the sets of the independent sets that make up your coloring will never change. And the way that we saw that was because this component induced by blue and green is connected. And so when you do a Kemp swap, it just swaps all the greens for blues and all the blues for greens. And it's the same thing here, green and orange, that subgraph is connected. And what do we say? Blue and orange, that subgraph is connected. And it's the same thing over here. So now when you come to this one, it's the same principle. So now we just want to argue that every 2-colored subgraph, or every subgraph that's induced by 2 color classes is again connected. And then when you do the Kemp swap on it, you won't change any of your color, you won't change the independent sets you use in your coloring. You'll change which colors show up on which independent set. And so the fact that the subgraphs are connected for green and blue, or orange and blue, or orange and green, that's just the same as it was before. So now what we're really interested in is just looking at these, the pairs that involve red as one of the colors. And you can see here we've got red, blue, red, blue, red. Or we've got red, orange, let's see, red, orange, red, orange, red. And the same, it's red, green, red, green, red. And so because those subgraphs are connected, when you do the Kemp swap, you don't change. And then this is basically the same thing here. There's sort of like a little bit of a mirror going on, but it's the exact same argument here. So this constructs sort of two distinct four equivalence classes for this graph. A natural question is to say, can you get more than two distinct equivalence classes? So this is just what I said. And the answer is yes. So what you do here to can you get more is you sort of paste one of these inside the other one. So I understand that these pictures are a little bit hard to see, but what you've got going on is you just take one copy of one of these and paste it inside the other one along this triangle. So for example, you rotate this one on the right 120 degrees, what is that, counterclockwise, and paste it in here. And that would give you, I think, this one. So anyway, but what's the point here? The point is now you get four color classes that are four equivalence classes that are really, you can't move from any one to any other. And the reason is that all of the two-colored, maximal two-colored subgraphs in this one are connected. And it's true in this one as well. And so when you paste one into the other, those two subgraphs are going to share one of these vertices in the triangle that they're pasted along. And so what that tells you is that the subgraph induced by any two color classes in these bigger things is again going to be connected. And you can repeat this, and by pasting more and more copies inside, you can actually get arbitrarily many equivalence classes. So in a sense, this is saying these give you graphs that are very far from being four-ergodic, planar graphs that are very far from being four-ergodic. Okay. Right, that's what I just said. So what else? So Mohar conjectured that if G is K-regular, then G is K-ergodic. This is not true, but this is the only counterexample in the case K equals 3. So this was proved for K equals 3 by Figali, Johnson, Paluzma, except for this one counterexample that we saw, the prism over K3. And then a little while later, it was actually proved for all K at least 4 by a couple of the same authors and a couple of different authors. So that's a really nice result. It says that with this one exception, every regular graph has all of its, every K regular graph has all of its K colorings being K-ergodic. That's just, I like it. Now, in this paper by Bonamy, Bousquet, Figali, and Johnson, they asked specifically about the triangulated toroidal grid. And that's this picture here. And you can think of it as you start with the Cartesian product of 2 cycles. And so that will give you a quadrangulation where everybody has degree 4. And then you put in all of these diagonals that are parallel to each other. And people are interested in this because of applications in physics. This is called the Anti-Ferromagnetic Potts model. But so this graph is 6 regular. And so, so their result shows that this graph is 6-ergodic, right? And oh, I'll come back to this coloring in just a second. So they proved that it's 6-ergodic, and Mohar and Salas actually showed that it is not 4-ergodic. So they found 2 4 colorings that are not 4 equivalent to each other. And so the natural question then is this graph always 5-ergodic? And the answer that I proved with Reem is that basically yes. When the dimensions are each at least 6, this graph is 5-ergodic. So let me say briefly why I put this picture here. So this is a 4-coloring of the picture that you see. So you can think of as this is T7 cross 7, where each of the dimensions is 7. But this actually gives you, this picture gives you a very succinct proof of the fact that whenever A and B are at least 6, then this triangulated toroidal grid will always be 4-colorable. And the way to think about it is, for every integer that's at least 6, you can write it as a combination of 3s and 4s, right? So 7 is 3 plus 4, and 8 is 4 plus 4, and 6 is 3 plus 3, and then after that you add multiples of 3. So what that means then is, if you have an A by B grid, you can chop it up into rectangles that are 3 by 3 and 3 by 4 and 4 by 3 and 4 by 4. And then what you do to color it is you just take the coloring that rectangle gets in this picture. And then you have to check that on the boundaries, everything matches up. And in fact, it does. So that's a really short proof when both dimensions are at least 6. And we'll want that later, that these graphs are 4-colorable. And actually, what Reem and I proved is something more general. We don't actually care that this arises from the Cartesian product of 2 cycles, and then you add in the diagonals. It turns out that any 6-regular toroidal graph, where it's called the edge width, but it's the length of the shortest non-contractible cycle, as long as it's at least 7, then the graph is 5-ergodic. And it's sort of full disclosure, there's not a whole lot more that can happen than this picture here. So when you think about it, sort of locally, it's going to look like this. That's your only choice in a 6-regular graph. But globally, what can happen is sort of when you glue the top to the bottom, say you glue it, then before you glue the left to the right, if you want, before you just sort of glue it right away, you could shift it some. And it turns out that those are the only 6-regular toroidal graphs. So there is more that's going on than just this picture, but not all that much more. Basically, what we're saying is we care about the local structure, but we don't really care about the global structure. Okay. So again, let me just pause and see if there's, ask if there are any questions. No? All right, we'll keep going. So let me give you kind of a proof outline and talk about some of the pieces that go into it. So a good 4 template, so you can see it there. It's an independent set of size 4 such that identifying its vertices gives a 4-degenerate graph. And it appears in a coloring if all the vertices in that good 4 template have the same color. So let me just show you a picture. So this is an example of a good 4 template. So if you take whatever 6-regular toroidal graph that you like, and then you identify 4 vertices that have the same relative position as these 4, the resulting graph will be 4-degenerate. And I'll tell you why we care about 4-degeneracy in a second. But let's just walk through that real quick. So why is that? Well, the first vertex you can delete is this one, because he did have degree 6, but now 3 of his neighbors got identified. And so those 3 neighbors are just giving you sort of 1 neighbor now. So he drops down to degree 4. And then next you can identify this one. You can delete this one because he had 2 neighbors that were identified. So he dropped to degree 5, but one of his neighbors is already deleted, right? So now his effective degree is 4. And then next you can delete this one. because again, he has two neighbors that were identified, and he has one neighbor that's already been deleted. And then once you get these three deleted, then you can sort of go up and just delete sort of everything at this point, because now this one, you can delete him because he has two neighbors that are already deleted. And then this one you can delete because he has two neighbors too, and this one that are already deleted. And then this one and this one. And so you can just kind of like run across the columns and down the columns and across the rows, and you can just delete everything. So this is an example of a good for template. I'll show you one more. This one, maybe not surprisingly, it looks pretty similar, and in fact it is. It's the same thing, except that the relative position of this third one is a little bit different, but of this fourth vertex in the good for template, but the argument is exactly the same. So why do I show you both pictures? Because these are in fact the only good for templates, sort of up to rotation and reflection, right? So the six regular, so the triangular lattice has some obvious symmetries under rotation and reflection. And obviously, if you apply those symmetries to either of these things, you'll get another good for template. But apart from those obvious symmetries, these are the only two. And they end up playing a big role in our proof. So again, here's the theorem that we tried to prove, or that we did prove. Here's the theorem that we did prove. If G is a 6 regular toroidal graph and each non-contractible cycle has length at least 7, then G is 5 ergodic. So there's sort of 3 steps. The first one is to prove that all 5 colorings of G containing a good for template T are 5 equivalent. And remember, 5 equivalent just means you can walk from one to another by a sequence of Kemp swaps, never using more than 5 colors. And this is really kind of, this is what motivates us to be interested in templates, right? So why is this true? And it really goes back to that lemma of Las-Vegas and Meyniel. In particular, we're interested in the case where you're talking about 5 colorings. And so you would be talking about 4 degenerate. So you say, if a graph is 4 degenerate, then all of its 5 colorings are Kemp 5 equivalent. That was one special case of that lemma. And so what we're going to do here is, if we have some coloring that contains a good for template, that means that it's got, so it's either this one here on the left or this one here on the right. You've got these 4 vertices that are sort of this position relative to each other, and they all have the same color. And so now what you're going to do, you can think of just identifying, gluing them all together, and then the resulting graph is 4 degenerate, as we just proved, right? So by the lemma of Las-Vegas and Meyniel, all of the 5 colorings of that resulting graph, that slightly smaller contracted graph, are going to be 5 equivalent, right? And so then the only thing we have to do is we just say, okay, so how do we now lift that back, the fact that they're all 5 equivalent, lift it back to the original graph? And the point is just that you can use exactly the same Kemp swaps in the original graph that you used in the contracted graph. The only caveat is if you had some Kemp swap that involved the contracted vertex. So these 3 vertices go down to a single vertex in the smaller graph. And if you have a Kemp swap that involves them, then in the bigger graph in G, you might have to simulate that one Kemp swap with as many as 4 Kemp swaps. You do that Kemp swap for each of the components containing one of these orange vertices. And that's really it. So that's the whole proof of this lemma. But that's really nice. So basically, now what we want to do is we want to first of all, we want to get a coloring that has a good 4 template. And then we want to be able to show if I have a good 4 template here, and I have a good 4, then I can get to all of the other colorings that contain it. And then what if there's a different good 4 template? I want to be able to move to those colorings as well. And so that's the next step, is given good 4 templates T1 and T2, there are 5 colorings Phi1, Phi2 that each contain that guy, and they're 5 equivalents. So let me maybe draw a picture here. All right, so so it is the picture makes sense. So T1 is a bunch of, this is a bunch of colorings that all contain the good 4 template T1. So they have some copy of T1 where all the vertices in it have the same color in that coloring. And this circle is to indicate that they're all Kemp equivalent, right? And the same thing is true for T2. And so this circle here, this is 0.1 in the outline. This line here is 0.2 in the outline, right? This is saying there's somebody from T1 that can get you over to T2. And then, so how do you prove this? So this is actually even easier to prove than the first one. So what we're going to do is we're going to use the fact that these graphs are 4 colorable. So you take some 4 coloring of the graph, and now you pick some other color that's not in that 4, that's not used in the 4 coloring. So say green is not used in the 4 coloring. So what you're going to do is you take your 4 coloring, and then you find your good template T1, and you're just going to go one by one and recolor all of the 4 vertices in T1 with green. Okay, and obviously that coloring that has those 4 vertices colored green is equivalent to the coloring that's just the 4 coloring, because it was just 4 recoloring a single vertex, which are Kemp swaps. And then similarly, you could do the same thing with T2. You have 4 vertices that show up in T2, and you could go from your 4 coloring and one by one just recolor the 4 vertices in T2, again with green. Okay, and so now to get from some coloring that includes T1 to some coloring that includes T2, you just go one by one. First of all, you take green T1 and everything else in the colors of the 4 coloring. And then one by one, you recolor these guys to match the 4 coloring, so they go away. And then one by one, you put in these guys to match this 4 coloring. So that's it. So that's this proof of number 2. And then, so steps 1 and 2 are both like really not very hard. Step 3 is really where the work is. Oh, let's hold on to that for a second. So step 3 is really where the work is. And step 3 shows that every 5 coloring is equivalent to a 5 coloring containing a good 4 template. And so maybe the way I would show this in the picture is I would say that sort of like everything goes into here or into here, or maybe there's something else that's T3 down here, and everything feeds into one of these, right? And if you want to really be try to make the picture carry a lot of information, maybe what you would say is you have this one magical coloring in the middle that's the connector, and this here is the 4 coloring, or A4 coloring. And to get from any coloring with that's to get from any equivalence class based on a single template, you sort of go through this 4 coloring in the middle, and then you can go out to any other template. So The thing to say, so steps 1 and 2 are really quite easy, but step 3 is hard. And so this is like most of what the paper is about, is how to prove step 3. Okay, so let me just wave my hands a little bit about how the proof of step 3 goes. So I'll show you some pretty pictures. So the idea is something like this. You want to prove, so I call this a good triple. So you want to show that if you have a triple, so this is three neighbors with a common neighbor, 3 vertices with a common neighbor that are pairwise non-adjacent. This is going to be the basis for one of your good 4 templates. And so what you want to show is that if you have a good triple in your 5 coloring, then you can actually do some Kemp swaps and get to a good 4 template, which is sort of, it's these arrows in this picture saying, maybe I don't have the template, but I can get into the template, get into something that has the template, right? And so that's basically what this paper is about, is showing you can always get to one of these guys that contains a good 4 template. And so basically the idea is you sort of say, well, you've got 1, 2, and 3 that are orange. If 6 was orange or 7 was orange, that would be a good 4 template. That's the same picture we saw before, just kind of rotated a little bit. And then if 9 or 10 was orange, that would be as well. That's the same picture, just reflected. And you can go through in 12, 13, 15, 16, and so on. And then you have to do a little work to handle what goes on with 8, 14, and 20. And eventually you conclude that 4 must be orange, and then you do a few Kemp swaps and you get there. So that's kind of the general idea. This is another picture. I call these parallel pairs. So if you have sort of 1 and 2 that are blue and 3 and 4 that are green, 1 and 2 that are green and 3 and 4 that are blue, then you can make some arguments and eventually conclude that you can get to a good 4 template. All right, so let me sum up. So we're interested in when are 2 K colorings K equivalent, which means you can walk from one to the other by a sequence of Kemp swaps. And in particular, we want to know, when is this triangulated toroidal grid 5 ergodic? And the answer is basically almost always. And one of the key pieces that we use in the proof are these good 4 templates. And the idea is that once you identify these orange vertices, then the graph becomes 4 degenerate. And once it's 4 degenerate, then it's an easy inductive proof to show that all of those colorings are equivalent. So that smaller graph after the identification is 5 ergodic. And then you lift those Kemp sequences in the smaller graph to your original graph that shows that a whole bunch of your colorings of the original graph are Kemp equivalent. And what we actually proved is that if G is a 6 regular toroidal graph and each non-contractible cycle has length at least 7, then G is 5 ergodic. And it has these 3 steps. The first 2, I really gave you like basically the whole proof. And then the third one is where a lot of the work happens. I guess one thing, so in the title of the talk, I said most. I said all 5 colorings are Kemp equivalent for most 6 regular toroidal graphs. So let me just maybe explain that a little bit more. So this each non-contractible cycle has length at least 7. This happens almost surely. So if you like probabilistic statements, then what this says is as n grows, if I pick such a graph, 6 regular toroidal graph on n vertices, then with probability going to 1, it's going to have all the non-contractible cycles of length at least 7. So basically, then that means that we'll get our conclusion for almost all of these 6 regular toroidal graphs. So let me stop there and take any questions.
Well, let's unmute ourselves and thank Dan for the talk.
Yeah, thank you.
Any questions?
Dan, can you give us an instinctive idea for why you would want to seek out the templates?
Yeah, so I mean, I guess the instinctive idea is when you have, so the instinctive idea is that you have that lemma of Las Vegas and Meyniel, right? So basically the point was we know how to handle graphs that are 4 degenerate, right? And my 6 regular graph is obviously not 4 degenerate. But it's sort of not very far from being 4 degenerate in the following sense. If you're allowed to cheat with a few vertices at the start of your vertex order, then after that, it gets to be 4 degenerate, right?
Yeah.
And so that's what the 4 templates are sort of formalizing, that notion that like, okay, it's not really 4 degenerate, so we can't just apply the lemma. But it's like, it's really close to being 4 degenerate, right? And so if you could just kind of get over this hump at the beginning, then you'll be fine. And so that's kind of the intuition that motivates that definition.
Thank you.
Yeah.
Because, yeah.
I have a question. So you have toroidal graphs. How is it with graphs that are, say, on Klein bottom? It's kind of they are somewhat similar, a little bit. Maybe it's stupid question.
Yeah. No. It's not a stupid question. I have to think about it. So I'm not as familiar with this, with the characterization, but I suspect that I could do something similar. Because like I said, we really don't need the fact that we don't need the global structure at all. All we care about is the local structure, right? And so it wouldn't surprise me. I'd have to go and look at it to be sure, but it wouldn't surprise me at all if the same proof just goes through. The question was about that we came to was about these particular graphs that are toroidal, and so we kind of started there and focused on that. But I think probably so. With the Klein bottle, the max average degree of the Klein bottle graph is at most 6, right? And you can have equality. So I think it would be the same thing. Yeah.
Maybe the only thing is if you can find the for coloring, right? If everything is local, the for coloring is the only global thing.
Yes.
You have to check if the rest will work.
Yeah. So that is true and not. So you don't need the full power of 4 colorability. 4 colorability is great, and it makes it really easy. But one thing that I glossed over.
You can like stitch it on the same boundary that is far
Yeah,
from
I
the
mean,
template.
essentially all you need is you need it to sort of be 4 colorable around the place where you have these 2 templates that you're trying to move between.
You can use the 5th color on the boundary when you are stitching it together.
So initially I had something that was a lot more complicated than this. Then my grad student was like, wait, couldn't we just do this? And I was like, yeah, that's a much better, like a much shorter way to do it. So so there's a lot of wiggle room of, you don't actually need 4 colorability. And in the paper, one of the graphs, so when I prove it more generally for the graphs that have edge width at least 7. That proof of 4-colorability doesn't go through. And in fact, they're not all 4-colorable. There's like one exception that's not. And we just kind of handle it ad hoc because there's a coloring, it's not 4-colorable, but it's like mostly 4-colorable. There's just like one place that you need the 5th color. And so we can just kind of put that 5th color in a place that it doesn't get in the way. So yeah.
Maybe if you page that little piece a little more, it will also give the quite better.
Yeah, that's worth thinking about.
More questions? Other questions?
So when I spoke in Bernard's class, I made all of the grad students ask questions. So I won't do that today, but I think it would be nice if anybody, it's just good to practice. And I'm not going to bite your head off. I'm not going to say that's a stupid question or something. So just give it a try and like, yeah.
Honestly, I was a little curious about with Bernard's question about the Klein bottle, how this sort of diagonal structure would wind up looking, how that would work.
That's a good question.
I mean, I guess it's not even so much a question as just a pondering. I'm gonna go home and draw it or something.
Basically what you want is you want to understand like what do 6 regular graphs look like on the Klein bottle. Yeah. I can tell you there's almost certainly a paper that answers that question exactly.
Yeah.
But I don't know it off the top of my head.
Mm-hmm. Yeah, no, that's fair. No, this is really interesting, though.
Thanks. So if you're interested in this kind of question, it falls into a broader scope of what's called reconfiguration. And it's you have an instance of something and another instance of something, and you're trying to walk from one to the other, where at each step you're allowed to make some small-ish modification and you want to get another instance of the thing along the way. And so in our example, the things are 5 colorings of this graph, and the step that you're allowed to do is Kemp swaps. But you could define this for all sorts of problems. You know, there's a version where you're talking about proper colorings and you're only allowed to recolor a single vertex. Or you could talk about, you know, these are dominating sets and you're allowed to add or subtract a single vertex. Or you could even talk about you have, you know, spanning trees and you're allowed to add one edge and subtract another edge. Now, spanning trees, if you think of them as graphic matroids, then of course you can get from one spanning tree to another. But if you put additional constraints along the spanning trees that you're allowed to have as you go, then you get more interesting questions. So there's all sorts of problems that have this flavor of, we have one, we're trying to get to another, and we want to make small steps that sort of maintain the goodness of what our solutions are. So, I mean, this is all kinds of applications. For example, you could think of like motion planning, where you have, you know, some stuff in a warehouse and you're trying to move a little robot around because he's got to go get your order from Amazon and take it to the truck so it can come to your house or something, right? So there's lots of applications of this, and it falls into this more general heading of reconfiguration.
Yeah, that's really interesting. Thank you.
Yeah, you're welcome.
Looks like there are not many more brave people. Let's thank them again. Thank you, then.
Yeah, thank you.